Otherwise, again, you can parse this by saying, well, show me the one based on the specific identifier. Okay, the identifier, you could say the tunnel number. But in our case, I said the role is the head end, which is me. Okay, it says that the path that we're using to go through is explicit path option is active. I'm not 100% sure why it doesn't show the full path there. Let's do this. Let's go to the tunnel and let me turn an auto route on to actually use it. Let's say tunnel, MPLS traffic engineering, auto route, announce. Show IP route for 2222, which is going out. This should change here in a second to the tunnel. Okay, so if we trace to 2222, this is going directly to that. So maybe I had a typo in the explicit path. Let's say show run or show IP explicit path. Yes, that should have said 1.2. Okay, not 1.12. Okay, so let's shut the tunnel down. Okay, do show run pipe section explicit. Okay, so let's remove it. So we want to exclude 10, 1, 2, 1, and 2, 2. Okay, then on tunnel 0, we'll shut, and no shut. Okay, so now it says it's going to 10 to 11, and then 10, 1, 11, and then finally to the destination. So it basically means that the traffic should now be rerouted in this direction. Okay, so on 1, if we look at the show IP route for 2222, okay, we have it installed over the tunnel, and we're going to trace to 2222. And it's going to XR1 and then back down. Now, when you're doing the backup tunnel, you don't necessarily need to configure a route out it. In this case, I used auto route just to test with the trace route whether the tunnel was actually formed and what the path that it's using. But since router 1 is not using this for locally forwarding its traffic, it's only using it to protect other tunnels that are forwarding through it. It's not required that you actually configure a route on it. Okay, so just to be clear about that, I'm going to remove the auto route. So we're not going to be using it for our local traffic. When we trace to 2222, this would go on the direct link between them once this gets removed from the routing table. Okay, so next we need to say, on that interface, if it goes down, what is the tunnel that we want to reroute the traffic to? So this is going to be on the physical link that we are protecting, which in this case is gig1.12. Okay, so on gig 1.12, we'll say the MPLS traffic engineering backup path. Backup path is tunnel 0. Okay, if we now look at the show MPLS traffic engineering fast reroute database, it should tell us that the tunnel that was sourced from the head end 11.11.11.11, which is this guy here, that is normally going on interface gig 1.12 is being protected. Okay, the status is ready, and if this link goes down, we're going to reroute it, and we're going to point it towards tunnel 0. Okay, tunnel 0 then, if we look at the show MPLS forwarding table, is going to point us towards, and I'm not actually sure if it shows it here. It doesn't show it because we're not installing it, but if we, again, show MPLS traffic engineering tunnels, where our role is the head end, it's going to reroute the traffic back to XR1, then down to router 2. But again, the key here is that the outgoing label is going to be a different value than it came in on. So the traffic is going to bounce back for one hop, but eventually it's going to go to back to the merge point, which in this case is router 2. Okay, so now let's see this in action. So what we're going to do is we go over to router 2, and we're going to shut the interface down. And before we do that, we should see the trace route is going to go in this direction. But once the rerouting kicks in, the trace route should go from XR1 to router 1, back to XR1, over to router 2, and then it should merge onto the original path of the tunnel. So on XR1, let's do a trace. Trace 23333. You see we're using the TE tunnel. Then if we go to router 2 and we shut the link down, and pretty much almost immediately, I'm going to try to do this pretty quickly here, pretty much almost immediately as soon as we shut down the tunnel and we do the trace on XR1, it should learn the new path, which is this one. So the amount of time that it takes to switch over is going to be how long does BFD take to realize that the neighbor is down, and then how long does it take to program the new forwarding entry. Now, in a real hardware-based platform, like if this was ASR 9K or ASR 1008 or something, it would have already pre-written the label value at the line card in the hardware, so the switchover time is going to be very, very fast. In our case here, I'm running this on an overloaded ESXi host that's running everything on the single CPU, so it does take a little bit for it to actually figure out BFD is down, revoke the old label, and then install the new label. But we can see the path now is following that repair path. So again, it's kind of weird from a traffic pattern that it goes out to router 1, comes back into us, and then goes to router 2. But the difference here is that we now have this new transport label. This is essentially the fast rerouting label. Now, if we were to look at the debug from XR1's point of view, it's going to be constantly trying to recalculate this tunnel because the explicit path end-to-end is no longer valid. The problem, though, is that I did not give it a fallback dynamic path to say that we can no longer go from router 1 directly to router 2 because the link is down between them. So you do kind of have to be careful if you're using that debug that I showed, which was to debug the path lookup. If we run this on XR1, it's going to be showing the output over and over and over, which is debug MPLS traffic engineering path lookup. And it should tell us here that the path calculation is failing because we no longer have a direct link that is between router 1 and router 2. Okay, and actually this is going to depend on how often it is going to re-optimize as well. So let's say, there it is there. So it should tell us that there should be an error message in here somewhere that it's failing. But if we look at from XR1's point of view and show MPLS traffic engineering tunnels, and let's say for protection, tunnel protection, it says that our tunnel was protected. Okay, it was protected by the midpoint, which was router 1. Okay, there's a couple questions here. I have the original explicit path from XR1 to router 1 to XR2. I'm missing that in the explicit path. Let's see from XR1. Let's look at the show run or show explicit paths. It's included here. I think it was wrong before, and I fixed it. So it's going from based on what it's asking for here. It should be going from us to 1, 1 to 2, 2 to 12, 12 to 13, and then 13 to 3. But you're right that if I had said from XR1 to XR2, then this link protection would not need to kick in anyways, because it only happens if the traffic is being routed out that link to begin with. Now, the node protection is basically the same thing. The only difference is that when router 1 says it wants to exclude an address, it would be excluding the node value of 2222 as opposed to those individual link values. Okay, so let's say that we're going to do that in the reverse direction, that we're now going to have a tunnel that goes from router 3, and let's say router 3 is going to do kind of the same thing, where it's going let's say XR3 and then over to XR2, over here to, let's see, how could we do this? Because I'm going to need to do it from the iOS point of view. So let's say this direction. Let's go 3 to 2, 2 to XR2, XR2 to 1, and then 1 to XR1. And the node that we're going to protect against the failure is going to be this guy here. Okay, there was also another question. How many exclude statements do I have in the backup tunnel's explicit path? Right now I have 2, but technically you only need 1 because when the full path is enumerated, it shows your local address plus the remote address on the other end. So if we show MPLS traffic engineering tunnels where we are the role head end from router 1's point of view, it says that the traffic comes from me and goes to the IP address on the other end. Then it comes from XR1's IP address, it goes over to router 2, and then from router 2 it goes to the loopback. So the point being is that it shows the address on both ends of the link. As long as you exclude one of them, then it's fine. For clarity, I'm excluding 2 of them, but it's not really required if we look at the show IP explicit paths. Okay, so now let's do this again, the reverse direction. So on router 3, we're going to say we want to go from 3 to XR3 to router 2, XR2, and then kind of actually like this. Let me see, how would it be? So I want to protect against XR2. So let's say this direction, kind of out of the way. Okay, so let's define the explicit path. And actually, let's just look at one's syntax and then kind of copy this. Let's say show run pipe section explicit. Or actually, well, yeah, that's fine. Okay, so let's say from 3. IP explicit path, we'll say name is to XR1. And then the next address is going to be, we want to go to 13. Then we want to go to 2, then to 12, then to 1, and then the final destination. Final destination being 11. Okay, so on our tunnel, we'll say interface tunnel 0. Tunnel mode is MPLS traffic engineering. IP unnumbered from our loopback. Tunnel destination is 11. The tunnel MPLS traffic engineering path option is explicit, and the name was to XR1. Okay, if we see the line protocol come up, again, that means that the calculation was successful and we were able to signal. Okay, now I also need routing. So let's say tunnel MPLS traffic engineering auto route announce. If we now show IP route for 11, 11, 11, 11, we should see that it's going out the tunnel. Now tunnel 0. If we trace the path, okay, we can see we're using it. Okay, now right now, as it stands, this link is disabled on router 2, but this interface is still available. So we don't have any problems when we're going in this direction, because I went kind of a roundabout way. But we're not actually going to be able to reroute both of these at the same time, simply based on, or actually, let me think about this here. We actually should be able to if the traffic goes kind of something like this. So the protected path on XR1 is going this way. To 2, no, it went this way. We're charging per link, every link that the traffic goes out. Okay, then the reverse is the primary path is supposed to go up, then down, then up, then down, then over. But we want it to, from router 2's point of view, it's going to be the point of local repair, and then the merge point is going to be not the next hop, but what we call the next hop, the NN hop. Okay, the difference between N hop and NN hop is the link protection versus the node protection. So in our previous example, from router 1's point of view, its tunnel destination was router 2, because it's saying, I want to use router 2 as a node, but if one of the links goes down, reroute it in order to get back to merge us back onto the primary tunnel. But in this case, we're going to say that if the entire node goes down, if XR2 goes down, we want to figure out what would XR2's hop beyond it be in order to get us back onto the to the primary path. And you can see this, they do a pretty good job of explaining this in the documentation example, where they show some diagrams of what would be the next hop versus the next hop. And let's say here link protection, which is this one. Okay, basically in our case, this was router 1, this was router 2, and then the protected node that we went through was XR1. Okay, so it's still, we had the direct link between them, and then we rerouted that way in order to get to back to the merge point. But in the case of the node protection, in our case, this is going to be XR2, this is router 2, and it's going all the way around to remerge back on router 1, which is the next hop, or again, the in hop. Okay, what this means from a configuration point of view is just that the tunnel destination is different. So there's no CLI difference between a link or node protection. It's just you say, is the destination the directly connected merge point, or is it the indirectly connected merge point, which makes it the next hop? So it does take some, if you were to do this manually in a real design, it takes a lot of planning because you would have to kind of recalculate manually what are all the possible next hops. In most practical cases, though, there's some automation software that does this. So you can configure the routers to do auto single hops, which is like an auto backup tunnel feature, or you can do a calculation offline, like some sort of software that you put the shortest path tree graph into. It figures out what are all the different possibilities, and then it builds the tunnels automatically for you. I'm not sure if Cisco has a product that does that anymore, but they used to have one that was called the Tunnel Builder that does the automation for you. It might be part of Cisco Prime now. So anyways, let's go now to router 2, and we're going to do the same thing. Okay. Now this is going to take a little bit longer because we're not running BFD between router 2 and XR2, but it should be able to still detect the problem based on the ISIS hellos being lost. We could lower the interval between them, or we could lower the RSVP hellos, but in this case, we'll just leave it as the default. Okay, so on router 2, let's go ahead and create a tunnel, and actually I'm going to bring that link back up. Okay, so let's say we have interface tunnel 0, and the tunnel mode is MPLS traffic engineering. MPLS traffic engineering. The IP address is unnumbered from our loopback 0. The tunnel destination is router 1, which again is the next hop. Then the tunnel MPLS traffic engineering path option is going to be an explicit path. Okay, so we'll say an explicit path, and we'll call this the, let's say, node protection. Okay, so now we need to define the explicit path. So let's go to the tunnel and let me shut it down while we're doing that. So IP explicit path, the name is node protection, and basically the only thing that this needs to say is that we want to exclude the address that is 12.12.12.12. So basically I want you to get to router 1, but I want you to get to router 1 by not going through XR2. And in other words, it basically should just reroute it directly to that link. Okay, so let's go ahead into the tunnel. We'll do a no shut. Hopefully line protocol comes up, which is going to tell us signaling was correct. If we show MPLS traffic engineering tunnels where we are the role of the head end, it says the explicit route is directly over to router 1, okay, which is what we would expect. It's direct point-to-point between them. Okay, now we need to tell router 2 that if a tunnel is going out that link, we need to protect it for node protection to reroute over to router 1. So on router 2, we'll say that on interface gig 1.2.12, that the MPLS traffic engineering backup tunnel is going to be tunnel 0. Okay, additionally, router 3 at the head end, it needs to request rerouting. So this is where we're saying on its tunnel 0, tunnel MPLS traffic engineering fast reroute. So it's basically asking again the midpoints downstream, closer towards the destination, that if you are running rerouting, please include my tunnel as part of that calculation. Okay, so now on router 2, if we look at the show MPLS traffic engineering fast reroute database, it should say router 3's tunnel is protected. Okay, currently it's going out gig 1.2.12, And if that interface goes down, which basically it's either link or node protection, it's both at the same time, but in this case it's going to detect either of them. So if the node goes down completely, our previous case where we're trying to merge back onto that individual node wouldn't work. And what I mean by this is that if we look at the show IP or show run interface tunnel 0, where we're saying we're trying to get, if previously we said we're trying to get to router 2, and then we were protecting the link that was going to router 2, the problem would be is if that node is completely lost, there's no way for you to merge back to the node because it's no longer in the link state database, which again means that we're trying to merge it back to the next hop as opposed to the directly connected ones. Okay, so simply based on the fact that we're merging multiple hops away and that the IP explicit path says to exclude the entire node, that's what's making it node protection. Okay, so now let's actually see it in action. So from router 3's point of view, if we do a trace to 11, 11, 11, 11, we should see that we're using the path that we originally defined, which was that we're going from router 3 going to 13, then over to 2, then up to 12, down to 1, and then over to XR1. Okay, so next let's go to router 2, or actually XR2. And I'm just going to shut that whole physical interface down, okay, which is going to drop all of the sub-interfaces, gig 0000, shut, and then commit. Okay, then from router 3's point of view, we're going to trace this again. And notice here, it's going to take a while now because we're not running BFD. Once the ISIS adjacency is lost, then we should be able to resignal. And on router 2, if we look at the show MPLS traffic engineering fast reroute, it should say that, well, actually it's not going to do that because there's no hello that's registered with the TE. Actually, what I need to do is shut down the link on router 2 side because this is a logical link. It's not a true point-to-point link. Okay, so let's say on gig 212 we shut it down. Okay, if we were running BFD, that would have solved the problem because it tells the upper layer traffic engineering, hey, you need to start your protection. Okay, so if we look at the reroute database, it says now it's active. Okay, from router 3's point of view, when we now look at the trace, we see we're going from 13 to 2 and then 2 directly to 1. But the difference here, if we look at the previous label numbers that were used, router 1 was using label number 26. Router 1 is still using label number 26. So this was the one that was originally signaled. This is when we merged back onto the primary tunnel. But the link between 2 and 1 is using label number 30. If we go to router 2 and look at the show MPLS forwarding table and look at out label number 30, notice that it's not listed here as an LDP label. Okay, what it will be listed here, though, as the TE label. So if we show MPLS traffic engineering tunnels for where we are the role of the head end, we should see that the out label is going to be, which one did it send? It sent label 30, which is, let's look at the CEF table. Show IP CEF for, well, it's not installed in the routing table, so I don't believe that we're going to actually be able to see this. Let's look at the show MPLS traffic engineering fast reroute database. I think it'll say here in label 30. And then out label 16014, which is, well, technically we're not even using the out label because router 1 is the penultimate hop. So we're actually, router 2 is the penultimate hop to get to 1 because they are directly connected. What would be a little bit easier to look at this example, let me take a step back. So let's no shut and then commit. And then on router 2, we will disable this link and this link. We should see that the protection goes that way and then comes back. And we'll be able to see the additional label in the stack. So from router 2, let's say that on interface gig 1.12 is shut down, and interface gig 1.212 is also shut down. And if we now go to router 3 and do the trace, we're going from 2 to 12 to 2. And let's think about this. So it's going, let's see, actually 3 is not using that tunnel now, which is, let's see, why would it not be able to use that? I think there's too many failures is what it is. So we're saying 13 to 2, which we can satisfy that currently. 2 to 12, we cannot satisfy. So let me try bringing one of these links back up. Okay, now the tunnel is up. Let's look at router 2 and look at the show MPLS traffic engineering fast reroute database. And it now says, okay, status is ready. So let's say that interface gig 1. Let's see, I think I'm going to need to shut this down on router 2's side, 212. Okay, if we look at the fast reroute database, it says now fast rerouting is active. So from router 3, if we trace, now we have the additional label. So again, it's from a forwarding point of view, it's a traffic loop, but it's not an infinite traffic loop. Since when we go from the router 2 here, this is the point of local repair, we get onto the additional the FRR tunnel, we go back to the merge point, then from the merge point we're joining the original tunnel, which is bouncing us back to 11 again. So again, it's kind of similar to that example we looked at in L3VPN inter-AS option C, when the route reflector, if it's in the data plane, you can label switch to the route reflector and then label switch back again through the same hops in order to get to the destination PE. But it's okay to do that because you're on 2 separate label switch paths. In the case of L3VPN, that was based on changing the next hop value. In this case with TE, it's based on whatever the destination of the original tunnel is, and then what the destination of the backup tunnel in the intermediary is. Whether it being the directly connected neighbor in the case that we're doing link protection like router 1 to router 2, or whether we're doing node protection as we're going like from router 2 back to router 1. Now, beyond this, there are a lot of other minor things that you can do with traffic engineering, but what I would recommend to do is once you get to the point where you're comfortable with the basic configs in terms of making sure that RSAP is on all the interfaces, that T is enabled globally, T is on all the interfaces, and it's enabled under the IGP, either OSPF or EHRP, and then doing the basic tunnel setup. Beyond that, most of the stuff, as long as you read through the documentation and you know that you can do that with the feature, you would be able to reference that in the exam time if they were to ask you those type of questions. So what I mean by this, for example, if we were to go back to the main iOS documentation, and let's go to the MPLS config guide, path and link node protection, and then some of these things like auto tunnel primary. Okay, basically the idea of this is like the name implies, it's going to create the tunnel automatically for you. So it does backup tunnel, you can do it for link protection or you can do it for node protection. It says a primary one-hop auto tunnel enables a router to dynamically create one-hop primary tunnels on all interfaces that have been configured for TE. But from a configuration point of view, if we look at how to do it, those are the verifications. Where's the config? You do it in global config. MPLS traffic engineering auto tunnel primary. And then you say, like, what's the number of tunnels that you're going to use? Okay, this is like the interface number. And then there's some other timers and things that are related to it. This says, what are you going to use as the IP address? Okay, this would be normally like your loopback. And then it says also, do I want to enable LDP or not? And in what case would we need to enable LDP on the TE tunnel? Okay, remember that's when we're going from PE to P, P to PE, or P to P. So not end-to-end, not from PE to PE, and we're running L3 VPN or we're running L2 VPN as a service over the tunnel. Because in that previous example we looked at, when penultimate hop hopping happens one hop too soon, the problem is that the core of the network doesn't know the VPN label. Either the VPN label from L3 VPN or the VPN label of the pseudo wire, which would be for your point-to-point Atom circuit or for like your VPLS.